An object is launched from a height of 5 meters and lands on an adjacent ledge 5 meters high. If the object was launched 42 degrees at an initial rate of 27, determine A, time of flight, B, the time required to reach max height, C, max height achieved by the projectile, and D, horizontal displacement. So here's my diagram. I just want to emphasize a few things and offer a few suggestions. First off, notice my y-axis and my x-axis. Notice how it's proper to put my y-axis at the very end of the first ledge. Notice how I labeled my axes. I actually call my vertical axis y final as a function of time. This just reminds myself that at each point along my trajectory, my parabola, I have a different y value. So there's actually multiple y final values. However, the y initial only occurs here at the ledge of the first building. The initial height is constant. And again, looking at my x-axis, I labeled it x final as a function of time. Again, that just means there's different values of distance, different x coordinates at each point in time. A lot of people just simply label their x-axis x, but then they end up labeling their distance x. So I wanted to distinguish between my range and my x-axis. So yeah, just a suggestion, or if you're wondering why I labeled it that way, that's the reason. So looking at the time of flight, here's the kinematic equation I used. Y final minus y initial equals VI sine theta t plus 1/2 gt squared. I plugged in the final height of 5, initial height of 5, my velocity, and my angle. And let me just continue. The left-hand side is 0. For the first term, I get sine 42 times 27. 18.1 t. The second term on the right, negative 9.8 divided by 2, or you could say times 0.5. This gives 4.9 t squared. Next, the most common mistake that students make is, well, they say, what if I can just simplify this equation by dividing each term by t? Well, this eliminates one of your t variables, and it simplifies the equation to a linear equation. Now, this isn't proper, though, because then we eliminate one of our t values. So we eliminate one of our solutions. But all quadratic equations should have 2 solutions. So what you should do is factor out a greatest common factor of t. So you get 8.1 minus 4.9t. Again, don't just divide both sides by t at this point. Instead, use the zero product rule. If both of these factors are multiplied to equal 0, then it must be the case that the first term equals 0, or the quantity in parentheses equals to 0. So we stopped at t equals 0, or we could say negative 4.9t equals negative 18.1. So the 2 values for t should be t equals 0, or t equals negative 18.1 divided by negative 4.9, which gives 1. No, which gives, let me make sure, 18.1 divided by 4. About 3.69. So your time of flight is 3.69 seconds. It's always the larger of the two values, especially if one of the values for t is negative. You always reject a negative time. Good, so for part B, oh, and even before part B, here's another way of doing it. If you prefer to just do the algebra first and plug in numbers last, here's the alternative. Well, it's the same exact process, just, yeah, plugging in numbers last. I don't want to confuse you though, so if you want to move on and fast forward through the video, that's fine too. But again, what we really had was we knew the left-hand side would become 0. Because it was 5 minus 5. So then we do the same exact process. We factor out a t. Next, we set both factors equal to 0. So we say the first factor equals to 0, or the expression in parentheses. Perfect. Next, we subtract negative vi sine theta to both sides. And then to isolate t, we multiply by 2. And we divide by g. And if you plug in the numbers, you'll get the same result. So now time for maximum height well, the time required for maximum height, some people call it the half time. So this is simply the total time found in the previous step divided by 2. But remember, this only applies if the parabola is symmetric. So this process doesn't always work. So we take the total time and divide it by 2. And we get 1.85 seconds is the half time. The time required to reach the maximum height, or the y coordinate of the vertex. Let's look at an alternative way to do this. You could have also used this kinematic equation. The final velocity in the y direction equals vi sine theta plus gt. Then you look back at the diagram. And notice this is a special point on the parabola. So if you wanted to see the velocity in the vertical direction at the vertex, notice that the velocity at a later point in time in the vertical direction is 0 at the vertex. Because at this instant in time, yeah, the velocity vector is perfectly horizontal, so none of it is inclined at an angle. None of that velocity vector is vertical. So again, this only occurs at the vertex. So if you use that fact, well, you can find the corresponding t value at the vertex. So again, specifically when velocity is 0 in the vertical direction, we have the time at the vertex. So we get, well, we could subtract vi sine theta to both sides. And this is equal to g times the half-time. So then if we divide both sides by g, we get negative vi sine theta divided by g equals the half-time. And if you plug in the numbers, you'll get the same result as we did here. Good. So moving on to part C, that would be the maximum height. Let's see. So for part C, the maximum height achieved by the projectile, well, as we said, that should be the y coordinate of the vertex. So we can do y final minus y initial equals vi sine theta t plus 1/2 gt squared again. And then we can remember that, okay, well, y final isn't a constant. There's multiple values for y final at each point in time. Remember, technically, y final is a function of time. So this means that specifically evaluated at the half-time, yes, if we evaluate this y coordinate at this particular value of t, this should be the maximum height, the y coordinate of the vertex. So that's why I like to use function notation. It just reminds myself, like, okay, I knew y final was 5, but what students really struggle with is that there's multiple y final values. So they're like, wait, I can't use this equation to solve for y max. This says y final. Y final is when I landed on the ledge on the right and I knew y final was 5 meters. Well, no, this isn't a constant. There's multiple y final values because it's a function of time. So I'm allowed to relabel this as y max if I evaluate t specifically at the half-time. So again, this gives me y max would equal, well, I can add y initial to the other side. Y initial was 5.00. And then I have my v initial, sine of my angle in degrees, times my half-time, which was my 1.85. Plus 1/2 g, which is negative 9.8, times my half-time, 1.85. Oh, and I'm so focused on choosing different colors and writing in a neat manner, I almost forgot this is the half-time squared. So another most common mistake. So y max should be my first term plus my second term. When you type this into the calculator, the second term should be 33.4 plus my third term, which is going to be negative 16.8. So your y max should be 21.6 meters. Perfect. So let's just look back at the diagram and make sure that makes sense. Again, that's 21.6. So if we go back at the diagram, we have to be careful too. Look at this here, because we have a symmetric parabola, and we could have looked at it as starting from the ground and ending on the ground. And if we did, well, we'd have a max height here. And throughout our calculation, that was our let's see. This is about 16.6 meters here. And then the height below, oops, the height below is our y initial, which we already knew was 5 meters. So you can kind of go back and check your work and see if it makes sense. So I just want to emphasize, because a lot of students would simplify the scenario and they'd say, wait a minute, I start out at a height of 5, but then I land at the same height, which gives me a height difference of 0. So again, I could simplify the situation, and I could see this as starting from the ground, landing on the ground. My left side will be 0 either way. So yeah, just keep in mind that if that were the case, if you did approach a problem that way, you would get a height of 16.6, and then you'd have to remember, I have to add that height to my initial height above the ground, which is 5. So yeah, just a thing to keep in mind. And let's see. And yeah, so notice how we had this initial height on the left side, and we end up adding it to the right-hand side. So yeah, again, if your initial height was 0, the sum of these two numbers should give that red height in our parabola. Let me see real fast. That's 33.4 minus 16.8. That gives me 16.6, the red height in our parabola. So again, just saying, if you forgot to include that initial height, that's what would happen. You'd have your 16.6, but then you have to add your additional 5. So anyways, let me stop over explaining like I always do. For the last part, let me see. I'd just like to mention before we stop. Oh yeah, so there is an alternative way to calculate that again, just to check your work. Or you could have tried doing v final y squared equals v initial squared sine squared theta plus 2g times the height difference. So again, specifically at the vertex, we know the velocity in the vertical direction is 0. So specifically when v final y is 0, this is the maximum height. You could subtract vi squared sine squared theta to both sides, and this equals 2g times the height difference. Next, to isolate y max, you would divide both sides by 2g, and then you would add that initial height, and this would equal your y final, which is specifically your maximum height. And then you just plug in the numbers. So that's another great way to approach the problem. And you'd get the same result. So finally, the easiest part, part B, would be the horizontal displacement. Keep in mind, in physics, this is also called the range. And that's confusing because, again, in math, the range is the set of y values on your graph. But in physics, range means your horizontal distance, so your distance along the x-axis. So anyways, the equation is x equals vi cosine theta t. Actually, let me be more proper because I want to be consistent with my labeling. The proper way to do it is x final minus x initial. But 99% of the time, x initial is 0. So again, it's just more proper. It's a good habit. Remember, a lot of people just write x equals, and then you just remember x is your x final. Good. So we get x, or more specifically x final, should be v initial times cosine of 42 degrees times time, which was 3.69. So the range should be cosine 42 times 27 times 3.69. So the object moves about 74.0 meters to the right. Excellent. So that concludes our video on projectile motion. I really wanted to focus on the subtleties. So if you're really detail oriented, if you like to distinguish different scenarios and understand the purpose of a lot of the notations, I highly suggest this video. If you're comfortable using the different symbols and you don't really encounter these nuances, well, that's fine too. And maybe you wouldn't want to sit through this whole video. But yeah, just keep in mind, a deal breaker is a lot of professors just write the left-hand side as y equals, and it's pretty confusing. So just keep in mind a more appropriate way, the full equation is actually y final minus y initial. Likewise, the equation we used last for horizontal displacement should be x final minus x initial. So just in case you have multiple heights to distinguish between, you might want to use that labeling. And label the axes as I did as well. So anyways, that concludes the video, and take care.